This is AP Calculus AB, and we're going to be talking about the mean value theorem. Previously, we discussed Rolle's theorem, which says if your function is continuous on a closed interval, differentiable on an open interval, and the endpoints of the closed interval are the same height, then there's guaranteed to exist a value c on the open interval where the instantaneous rate of change is equal to 0. So there's got to be a critical value found by setting f prime equal to 0. Well, the Rolle's theorem is actually a specific case of the mean value theorem. So let's discuss the mean value theorem. As long as a function is continuous on the closed interval and differentiable on the open interval, then there has to be at least one time where the instantaneous rate of change is equal to the average rate of change. Average rate of change has to equal the instantaneous rate of change. That's what we're saying. So like, for example, I don't draw this, but let's say that we were finding a secant line that went through these 2 points. Then what this theorem is suggesting is there has to be some place where there's a tangent line that's parallel to that. And you can see how that just worked. Let's pick a different pair of points. Say we just pick these 2 points. So that's a secant line. If I wanted to find the slope of that secant line, that's the average rate of change. If I were to take a parallel line, there has to be some place where it's tangent to that, to the curve. It's essentially what the mean value theorem is saying. So let's see if we can figure out when we can use this and see if we can look at some examples. Consider the function h of x, which is pictured. A, does the mean value theorem apply on the interval from -1 to 5? So first of all, you're allowed to use MVT for mean value theorem. Well, in order for this to apply, it has to be continuous. But I think that we would agree that h of x is undefined at x equals 0. Because if x was 0, this function would be 5 divided by 0, which is undefined. Therefore, h of x is not continuous. Keep in mind, it doesn't have to be continuous everywhere. It just has to be continuous from -1 to 5, and 0, where it's discontinuous, is part of that domain. Therefore, the mean value theorem does not apply. B, does the mean value theorem apply from 1 to 5? Well, from 1 to 5, the only place that's discontinuous is 0. 0 is not part of that domain. So we could certainly say that h of x is continuous on this interval. Is it differentiable on the open interval? Well, it sure is. I mean, it's pictured right here. We can clearly see that there are no cusps here. So we could say h of x is differentiable on the open interval. And that's all you need is those two things. Therefore, we would say the mean value theorem applies. And what does it mean when it applies? It means that if you were to find the average rate of change from 1 to 5, there would have to be another place in between these where the instantaneous rate of change was the same. See, graphically, what does the mean value theorem guarantee for a function on the interval from 1 to 5? Draw this on the graph above. Well, I'll tell you what, let's draw it first and then we'll talk about it. So I'm going to put a point when the x value is 1 on the graph and a point where the x value is 5 on the graph. I'm then going to draw a line that contains those. This, once again, is a secant. Touches the curve twice. If I were to draw a parallel line it would hit this curve in one location, it would be something like this. This would be the tangent. Now I can't tell for sure by looking at this graph what that actual point is. It doesn't look like it's an integer. But this point here, this x value, we're saying that x value is c. So graphically, what does this guarantee? The mean value theorem guarantees a value of x equal to c where the tangent line drawn to c h of c is parallel to the secant line passing through (1, -2) and 5, 2. Now, when you're going to do the mean value theorem, it's not going to be so wordy. Right now, we're just trying to gain an understanding. Part D, apply the mean value theorem. All right, so here's what I suggest. So we're going to do this in 3 parts. 1, 2, 3 parts. This last part, we want to make sure that h prime is going to be equal to the average rate of change. That's what we're after. So in order to do this, we need to figure out what the instantaneous rate of change is. So that would be the derivative. So h was 3 minus 5x to the -1. H prime would be 5x to the -2, which I would prefer to write as 5 over x squared. So we're going to put that over here, and instead of writing an x, we're going to write a c. So it's 5 over c squared. If you chose to leave as an x, it'd be fine, but really the mean value theorem says it's some value c. So it's got to be equal to the average rate of change. Well, what's the average rate of change? That's going to be h of 1 minus h of 5 over 1 minus 5. Why am I choosing 1s and 5s? Because it says on this closed interval. This is the slope of the secant line. This is the same slope that you found in Algebra 1 when you were in 8th grade. According to the graph, h of 1 is -2, and h of 5 is +2. 1 minus 5 is -4. So -2 minus 2 is -4. -4 divided by -4 is 1. The average rate of change is 1. The mean value theorem guarantees there has to be a tangent line whose slope is also 1. And it's asking us to figure out where that happens. So we set the average rate of change equal to the instantaneous rate of change. We solve this equation. We get that c is plus or minus square root of 5. However, negative square root of 5 is not in the domain. So c has to be the square root of 5, which is between 1 and 5. That's why we weren't sure what this was. It was an irrational answer. This is the mean value theorem. It's this right here. But you have to know if it applies. So combining these two things is probably as hard as it's ever going to get with the mean value theorem. Let's check out some more examples here, and then we'll be done with these notes. Explain why you cannot apply the mean value theorem for this function on the interval from -1 to 1. All right, well, let's see. Is this function continuous? This is an x raised to an exponent, and it's a cubed root. There are no restrictions on cubed roots, So we could say f of x is continuous. This is not helping our cause because it says explain why you can't use it. So it must mean it's not differentiable at all places. But I don't understand why it isn't. So let's find the derivative. Using the power rule, I'm going to put 2/3 in front. Subtract 1 from the exponent. If I write this in, the derivative of -2. Derivative of -2 is 0. If I write this as a fraction, I get 2/3 to the 1/3. Now if we look here, is there any place on this interval where this derivative is undefined? And I would say definitely yes. F prime of x is undefined. When x is 0. Because if x was 0, I'd make this denominator 0. If f prime is undefined, that means it's not differentiable at that point. So therefore, f of x is not differentiable for all values of x on -1 to 1. Therefore, the mean value theorem does not apply. Find the equation of the tangent line to the graph of f of x on the interval from 0 to pi, at which the point, which is guaranteed by the mean value theorem. This, I think, really should have been capitalized. So I first need to figure out what c is. Okay, I got to find c, the point guaranteed by the mean value theorem. So I'm going to break this down to 3 parts once again. I'm going to find f prime here. I'm going to find the average rate of change here. And then I'm going to set f prime of c equal to the average rate of change. So the derivative of this is going to be 2 plus cosine of x. The average rate of change is going to be f of 0 minus f of pi over 0 minus pi. F of 0, 2 times 0 is 0. Sine of 0 is 0. So I got 0 plus 1 minus. If I put pi into this, I'm going to have 2 times pi. Sine of pi is 0. Then I have this 1. So it's going to be 1 minus 2 pi plus 1. On the bottom, I have negative pi. Now I wrote this in a way that doesn't look so hot. This is going to simplify to 1 minus 1's cancel. So I get negative 2 pi over negative pi. It's going to simplify to 2. The average rate of change is 2. So if I set 2 plus cosine of x equal to 2, average rate of change equals the instantaneous rate of change. Instead of x, I want to say c, because we're trying to find the c value. I could subtract 2 from both sides. And then when does cosine equal 0? At what angle? It's on the vertical axis, because we don't go left or right. Cosine is x over r. So that happens at pi over 2 and 3 pi over 2. 3 pi over 2 is not in this domain. So the only c value that works for this in the domain is pi over 2. We're supposed to find the tangent line. Find the equation of the tangent line. So to do that, I need a point of tangency. I'm going to need a slope of tangency. And then I can make my tangent line. To find my point of tangency, I'm going to take f and put into it pi over 2. So it's 2 times pi over 2 plus sine of pi over 2 plus 1. 2 times pi over 2 is pi. Sine of pi over 2, that's on the vertical axis, positive style. Sine of that's going to be positive 1. Plus the other one that was there, I'm going to get pi plus 2. That's my y value. So my tangent line is going to be y minus pi plus 2 equals the slope that I don't know yet, and x minus pi over 2. Just got to find that slope, and I'll have my equation. Find the slope, I'm going to plug into f prime, pi over 2. F prime we had up here, that's going to be 2 plus cosine of pi over 2. Cosine of pi over 2 is 0, so it's 2 plus 0, which is 2. And I guess I already knew that, so that was complete waste. This right here was a complete waste because we knew that already. Oh well. So that concludes the mean value theorem. And I just have it listed down here again from emphasis. Thank you very much.